context to, just to give context to everything. So I'm going to give a super high level overview. So the solar system originally started as a cold gas cloud, and what happened is the gas cloud began contracting due to gravity. As the gas contracted, it became denser and hotter, and eventually at some point it became so dense and hot that nuclear fusion was able to occur. And that's how a star is made. On the right side of the slide, you can actually see this happening in other star systems. So in the top right image, you can see the Orion Nebula, which is a giant cloud of gas that you can actually see with a telescope really clearly. And there's actually a bit of a zooming in pictures, I guess you can call it. And there's actually a small little dot at the center of the most zoomed in picture. And that's actually a little baby star. And actually in the bottom right of the image, yeah. And in the bottom right of the image, of the slide, there's actually a whole bunch of other baby stars that are also in the Orion Nebula. It's kind of neat. Yeah. You can go to the next slide. So you have a star, but what about all the leftover gas and dust? Because it doesn't all of it end up in the star. So due to angular momentum, the gas and the dust that eventually formed into a thin disk that's called a protoplanetary disk, and it's also spinning. Within that disk, particles of dust and gas can clump together due to gravity to form planetesimals. And then those planetesimals can clump together also due to gravity to form larger planetesimals, and eventually that process continues until we have planets. So on the bottom of the slide, you can actually see two pictures from different exoplanet star systems that are in the process of being made. At the center of the image, you would see the star, but it's been blacked out because otherwise it would be way too bright. You wouldn't see any of the detail. Yeah. And around the center of the image where you would see the star, you can kind of see a swirling disk, I suppose, of gas and dust, and that's the protoplanetary disk. And in the bottom left image, you can see a pretty clear bright circle in the bottom right of the bottom left image, I guess. And that's actually an exoplanet that's in the process of being formed. In the bottom right image, you don't see that same bright spot, but if you look closely towards the center of that image, you'll see a spot where gas is kind of swirling in on. And at that spot, we think an exoplanet is in the process of being formed. Now you can go to the next slide. Yeah, so this is just a quick video illustrating what I was talking about. Is it possible to get sound through Zoom?
Our solar system.
Oh, yeah, there we are.
Computer simulations allow us to reconstruct the formation of our solar system 4.6 billion years ago. We use the laws of physics to create these virtual experiments in order to figure out how planets took shape. After the sun ignited, most of the material around it had flattened into a disk of gas and dust. We can zoom into a simulation of a portion of the thin disk, a small piece of the universe in a box. Here, a dense swarm of objects clump together to form what astronomers call planetesimals. This simulation addresses how planetesimals form from much, much smaller particles, the size of pebbles. Pulled together by gravity, some planetesimals formed the planets, while others became asteroids and comets and dwarf planets. As the planets accreted, they carved out gaps in the disk. But the solar system remained quite cluttered. If we look at the orbits of the planets and accelerate the passage of time, so 1 million years pass by every 10 seconds, we can watch how the debris cleared. In this simulation, the giant planets, Jupiter, Saturn, Uranus, and Neptune, shift their orbits, and many unlucky asteroids and comets and dwarf planets get kicked out of the solar system. The migrating giants wreak gravitational havoc. The distribution starts out quite flat, but as most small objects get tossed out, others settle into stable orbits that allow them to coexist safely with the planets. But their orbits aren't as flat as the original solar system. Instead, they follow trajectories far above and below the plane of the planet's orbits. Today, the orbits of Pluto and other Kuiper Belt objects show exactly this pattern. The tiny icy worlds that inhabit the outer reaches of the solar system provide evidence for an ancient interplanetary transformation.
Right. So now that we have the star and we have planets starting to be made, we can talk about the planets themselves. So something we might notice when we look at the planets is that there's four main types of planets. There's rocky terrestrial planets that are close to the sun, and there's more gaseous Jovian planets farther away. And we might want to ask why this is. Well, the protoplanetary disk was very hot near the sun and very cold far away from it. Only metallic substances could stay solid near the young sun, so the inner planets are mostly rocky. The lighter elements like hydrogen and molecules like water stayed a gas at that temperature and were blown away by the stellar wind near the sun. Farther away, the planets could form out of the lighter elements as well, like hydrogen and molecules like water, because they were able to turn solid farther away from the star because it's cold. And that allowed those planets to be more massive. And because they were more massive than their closer in cousins, they were able to have a large enough gravity to attract large gas envelopes, which is why they're gas giants. We can go to the next slide. Yeah. But we also have a lot of leftovers, rocks and whatnot that didn't make it into planets. And those are the asteroids and comets that we see, as well as similar bodies that are left over from the formation process. And for the most part, they haven't been touched since the very beginning of the solar system. So on the top right and bottom right, you can see some examples of these leftovers. On the top right, there's a I think it's an asteroid. It's called Ultima Thule. It's about 20 miles across or so. And on the bottom right is actually a comet. And just for a bit of perspective, on the bottom left, it's the picture of the same comet on the bottom right, but to scale against Los Angeles, which you can see on the very bottom of the image, just to show its size. Yeah, you can go to the next slide. Right, so this was just a super high level overview. So there's a whole lot that we didn't cover, and I just wanted to briefly mention some of what we didn't talk about. So one of the things that we didn't talk about was why the original gas cloud that turned into our solar system started collapsing. So one of the main thoughts behind that is actually a nearby supernova. Actually sent out a shock wave, which caused the that gas cloud to start collapsing into our solar system. We could also go into more detail about how the gas and dust actually formed into planets. I remember when I first learned about this, I thought that it was really simple, I guess, that smaller rocks, clump together and those make big rocks, and those clump together and they make big rocks, and then eventually we have planets, and it all seemed really simple in my head. But actually, the more you look into it, it's actually incredibly complicated, and there's still a lot of open questions about that. So another thing we might look into is why the planets are so incredibly different. We went into a bit about why there's terrestrial planets and why there's gas giants, but Uranus is different from Neptune, which is different from Jupiter, which is different from Saturn by a pretty large amount. Venus and Earth, despite having pretty much the same mass and being super close, are super different in terms of their atmospheric composition. So we didn't cover that. We didn't talk about planetary migration, which is how planets that can form in one part of the solar system could have migrated to a different part, which is actually a major part of how solar systems are formed. And we also didn't talk about violence in the early solar system, how common collisions are and things like that, which is actually pretty important considering that that's how the moon was made. Because as you may or may not know, the moon was actually made when when the Earth was super young and it was still molten. It got hit by about a Mars-sized planet or planetesimal, I suppose. And from that collision, we had a bunch of molten rock that was in the Earth, but got sent out by the collision, and that eventually clumped together and turned into the moon. So so just to give an overview of what we didn't get to talk about in this high-level overview of how the solar system formed. So you can keep going with the presentation.
Okay, so I am, yeah.
You should be able to screen share now.
I'm going to talk to you guys about some of the largest rocks in the solar system, which are for the most part the terrestrial planets, and then the moon, of course. Now we're going to try to do this as a little bit of an activity. So if anyone, I'm going to ask you guys to try to point out some of the surface features you see as we talk about it. So if you want to chime in, just feel free to unmute and just shout it out. Make this interactive. So the moon is our first one to look at. And as Perry was just explaining, a little bit of its formation there, we see a lot of stuff, is a good way to put it, on the surface of the moon. So from this picture here, this is the moon that we get to see in our sky. Can anyone want to shout out some of the features they see?
Craters.
Yeah, craters. We got craters all over the place. Big one down here. This is called the Tycho crater. And there's another big one up here called the Copernicus crater. What else?
Isn't there the Sea of Tranquility?
Yeah, the Sea of Tranquility is here. That should be, I'm probably going to say the wrong area over here somewhere. Well, what about all this dark stuff? Does anybody know what all this dark stuff is?
Mare.
Yeah, Dan, the Mare. So this is interesting because the Mare it's actually a Latin name. It means seas, because when I believe it was Galileo first named this, because it looked like oceans to him, from standing on Earth. These are actually formed from lava flows, very ancient lava flows, and they're darker than the rest of the land, the rest of the area, because of the presence of iron in this area. So we can also tell a lot about the ages of these objects in the solar system based on what they look like. So an area that doesn't have a lot of craters, for example, the Mare here, we can tell is younger than an area with a lot of craters, let's say over here. So we know that the Mare and areas like it are going to be a lot younger, a lot newer surface than some of the more heavily cratered areas. Yeah. So another thing I wanted to point out here is these streaks that we see from these craters. So those are ejecta rays. So it's essentially when, an asteroid or comet, something impacts it and it shoots debris out in all directions around it. So you get those kind of like ray patterns. And you can see that with the larger of the craters over here and over there as well. Now, one question I have here is, why do we only ever see one side of the moon? This is the image that we all know and love, but somebody want to tell me why we don't see the other side?
tidal locking.
Yeah, exactly right. So the moon is tidally locked to the Earth, which, if you're not familiar, that means the moon rotates at the exact same rate that it revolves around the planet Earth. So we're only going to ever see one side of the moon. So for the thousands and thousands of years of human civilization, we have never seen the other side of the moon until we sent orbiters and stuff to it in the 1960s. So this is what the far side looks like. And we can see, tons and tons of these craters, much more heavily cratered than on the near side of the moon, the one that we see. Now, a lot of people think that's because the Earth helped to protect the moon from getting impacted on that side, but that's not the reason. It's more because of the lava flows that we see with the mare on the closer side of the moon. The Earth is very small, even in comparison. I think what I was reading only blocks out like 4% of the moon or something, so it's not a significant thing to help block any incoming asteroids and comets. Oh, another thing I should mention is, and I believe Perry talked about this when with the violent stage. So in the early formation of the solar system, when we had the heavy bombardment, it's about 4 billion years ago. The reason we see all these cratering, and most of them are very, very old, is because there was just so much violence in the solar system at that time that the moon and all the planets, all the objects were just getting constantly bombarded with all this, which caused all these cratering. So thankfully that's not something we really see anymore today, because obviously that could be very detrimental for life. Now, lastly, with the moon, we also see a lot, we'll see mountains on the moon, not very large, but these are formed from, the cratering, disrupting the crust and, causing all sorts of activity with there. There's no plate tectonics on the moon, and the moon is, completely solidified as far as we know. So there's nothing active going on that would be causing these. So that's made from some of the cratering. All right, another one of our objects is Venus. That's Earth's sister planet. So you don't really get to see much about Venus from this picture here, from the outside. And that's because Venus has a very thick atmosphere. So it's caused by a runaway greenhouse effect. Venus's atmosphere is mostly carbon dioxide, about 96%, which causes all the incoming, not all, but most of the incoming solar radiation to just be trapped on the planet and not be released. So it's very, very hot on the surface of Venus. It's like 900 degrees Fahrenheit on the surface. So it's very, very thick cloud, so we can't really see through it to the surface. There's also a lot of sulfur dioxide, which is why we get that yellowish color, which we'll see in a second. Now, Venus does not have plate tectonics. It doesn't have a floating lithospheric plate like we see on Earth with the moving continents and whatnot, but it is volcanically active. So we see still, even to this day, active volcanoes across the surface of Venus, which adds to, especially that sulfur dioxide being added to the atmosphere, just furthering that greenhouse effect here. So this is what I mean. This picture on the right is actually a picture of the surface of Venus. It was taken by the Venera lander, which was sent by the Russians in, I believe, the mid-'80s. It landed on the surface. It was able to be working for like an hour and a half before it just got destroyed under the immense pressure and heat on the surface of Venus. Because also the surface pressure of Venus is about, I think it's 9 times that of Earth or something like that. So really difficult to be standing on there. And we see some different rocks, but we don't see very many craters if we were to look at this picture here. Now, this picture on the left is a radar image, so that's how we were able to see through the really thick clouds. And we do see some craters if we look closely, like a couple over here, maybe something over here, down here, but they're not really, there's not a lot of them like we see on the moon or like we'll see on Mars in a couple minutes. And this is because Venus has completely resurfaced about, estimated between 300 and 600 million years ago. The surface of Venus was completely redone. And this is because, as I said, it's volcanically active. So all of this, this volcanism is causing the surface to be new. So the surface of Venus is actually pretty young compared to the surface of the moon and some of the other planets. And that's why, again, we don't see very many craters going across it. All right, now let's talk about Mars. And in the next slide, I'll ask you guys again to point out some of the features we see. But a little bit of overview of Mars. While Venus has a very thick atmosphere, Mars has a very, very thin one. It's also comprised mostly of carbon dioxide, about 95%. But it's, it's very, very thin, so it's not substantial like we see on Venus. On the poles of Mars, up here and down here, we see ice. Now, most of this ice is not actually water ice. It's mostly carbon dioxide ice, because the low pressure and the low temperatures on the surface of in the atmosphere of Mars are the right conditions to have ice, carbon dioxide ice, be frozen, like we see there. And we also see the reddish color. That comes from iron-rich soil, a lot of iron oxide there, so some rust is a good way to put it. All right, so this is an image of the dichotomy of Mars. So this is the entire planet, and this is a topographic map. So the red, on the left side of the color spectrum is the highest elevation, and to the purple on the right side is the lowest elevation. So again, what surface features, what things do you guys see in this?
A lot of the north is almost completely uniform.
Yeah, it's completely uniform in what sense?
It's very flat.
Yeah, it's very flat, and it's also a very low elevation. And I'll talk about that in a second. Oh, all right, let's talk about it now, and then we'll go back to it. So we see in the north of Mars, these are the northern lowlands, and in the south, the southern hemisphere is the southern highlands, and it's separated by this dichotomy here in the middle that I'm moving across with the pointer. And for the same reason why we don't see very many craters on Venus is the same thing we see here on Mars. This surface is younger up in the north because of its lower elevation, which we'll get to in a minute. So what else can we say?
There's a pretty noticeably low basin in the southern hemisphere.
Yep, that's right. This is the lowest point of Mars here. So that dips down pretty far in there. Mm-hmm. What else? Anybody got anything else?
Yeah, just which of the white, doesn't Mars also have the tallest mountain in like the solar system? Like which of the white peaks is that?
Yeah, so that's a great observation. Yes, Mars is home to the largest dormant or no longer active volcano, largest mountain in the solar system, and that's this thing right over here. That's called Olympus Mons, and it's in the Tharsis region of Mars, which is this whole region here. And we actually see a couple other volcanoes over here. Now, I'm going to ask the name of these volcanoes, but I'm going to specifically ask Connor and see if he remembers. Where's Connor?
I know the Tharsis Monte, and they're so big that they call it that little crack to the right of it. But as far as their names, I do not recall.
I know, I'm putting you on the spot there. All right, so we have Olympus Mons, which is the big one.
I'm a sedimentary guy, not a petrologist guy.
I know, but you were in the class with me, so I figured maybe. All right, so this one over here is called Ascraeus Mons. In the middle is Peronius Mons, and then Arcea Mons is on the bottom. And those are three. They're smaller volcanoes, but yeah, Olympus Mons is the largest. It's a shield volcano. We also see, which nobody mentioned, but this is a pretty famous structure here. It's called Valles Marineris. So this is about the size of the United States. And this is a huge crack. It looks like a channel. A lot of people think it was formed by water, but what we believe is because in the early, times of Mars, maybe 3.5 billion years ago, the crust was thickening in certain areas, and it caused this isostatic lift, which is essentially pressure put on the crust, which pushed it down and ended up cracking the surface, the crust, as we see over here. So we have this really cool, almost like a rip across the Martian surface there. And then again, all these craters, as I said earlier, there's tons and tons of craters across the bottom, so we can tell that's an older surface. And what this tells me is, being that the northern lowlands are younger, this is probably because we have all the volcanoes here, and it flowed downward to the lowlands and was able to resurface it while they were still active. But the volcanoes, wouldn't have flown south because that's at a higher elevation than it is in the north. All right, and Oh yeah. Then I also have this picture, so this shows you exactly what what it really looks like in its spherical form. You see Olympus Mons, the three other mountains, and the Valles Marineris across here. And lastly, this is a typical picture of the Martian surface. We describe it as a hummocky terrain, like very rocky, very rough and jagged. And this actually makes it very difficult for planning out missions to Mars because it's just so rocky and we can't really see this very well from our orbiters and the imaging from the sky. So it's hard to really tell where a good spot to land is. And that's one of the things we're going to try to do with the Mars 2020 is when we send the helicopter, which I talked a little bit about last week, to use it to see where a good area for the next, future missions of Mars to land in. All right, and that's it. So I will stop sharing and give that back to you, Henry.
All right, let me pull my screen share back up.
Yes, AL, that's why Mars is red.
Thanks. Yeah, I just wanted to make sure.
Okay, can you see the presentation again? Yes, all right.
Yeah, it's
All
good.
right, so now we're going to go over a few different specific types of space rocks. So the first sort of group of those is meteoroids and asteroids. And there's a few different definitions of exactly what meteoroids, micrometeoroids, and asteroids mean. But the one that's most accepted, defined by the International Astronomical Union, says that micrometeorites are up to about 1 micrometer, meteoroids are between a micrometer and a meter, and asteroids are larger than a meter. So they're all kind of similar objects, and then these names just sort of divide up the different sizes of those. And asteroids are kind of an interesting classification because asteroids can actually include dwarf planets too. The dwarf planet Ceres, which is part of the asteroid belt, it's the largest object in the asteroid belt, is actually still classified as an asteroid. So asteroids can go all the way from, the size of 1 meter to, I think Ceres is around 900 kilometers in diameter. So there's a very wide range of the possible sizes for asteroids, but most are much smaller than Ceres. Most are sort of in that meter to 100-meter range. And they're typically rocky or metallic, which is kind of what differentiates them from comets, which we'll talk about in a second. But within the solar system, asteroids are mostly inner solar system objects. There's obviously the main asteroid belt, which is between Mars and Jupiter. That's where most of the asteroids are. That's where Ceres is. And those asteroids in the asteroid belt are thought to be left over from that protoplanetary disk that Perry talked about earlier, that disk that formed the whole solar system. So those asteroids in the belt are sort of those planetesimals that are left over and never formed into a larger planet. And there's a couple of theories about why the asteroid belt is still left there and why those things didn't form into a larger body. I think the most accepted one is that because Jupiter is so large, that the gravity from Jupiter kind of perturbed the asteroid belt, and it doesn't let anything big enough form. It kind of messes with the interactions of all those bodies in there. Because Jupiter is the largest object in the solar system except for the sun. So its gravity has a lot of impact on other nearby things. And then another main category of asteroids are the Trojan asteroids. And the main Trojan asteroids, or the most common Trojan asteroids, are the ones around Jupiter. And those are in what are called the Lagrange points around Jupiter, which is sort of a stable gravitational region where they can kind of travel in the orbit of Jupiter from about, I think it's 60 degrees ahead of Jupiter to 60 degrees behind Jupiter. And the Trojan asteroids don't always have to be around Jupiter. Trojan asteroids are just kind of any asteroids that follow in the Lagrange the Lagrange point of a larger body. And there have been some found around other objects too. There have been some Trojan asteroids found around Neptune. I think there's even one Trojan asteroid of Earth and maybe a couple of Venus as well. So there are some other Trojan asteroids, but most of them are in Jupiter's Lagrange points. And then there are a few other asteroids kind of between the main asteroid belt and the sun. Some of those are called near-Earth asteroids, which are the ones we look out for because they pose the most danger to us. Those are the ones whose orbits get close to the Earth, so they put us at the most risk for an asteroid impact. And there are about 14,000 of those near-Earth asteroids that have been found so far. So then another classification of small bodies within the solar system are comets. And comets are a lot like asteroids. They're kind of a similar size to most asteroids. None of them are as big as dwarf planets like Ceres. But comets, what distinguishes them is they're usually icier. They have more ice on the surface. And some of that is water ice, and some is other hydrocarbons and things like that. So they have a different makeup. They're not as metallic as asteroids usually. And that ice that's on the surface is what creates the tail that we see as the comet. And most comets don't have a tail all the time, actually. They usually have what's called an elliptic orbit, which means that part of their orbit, they get much closer to the sun, or sorry, an eccentric orbit, which means part of their orbit, they get much closer to the sun than the other part of their orbit. So rather than being a circle where it kind of stays the same distance from the sun roughly the entire time, most comets get very close to the sun and then very far away from the sun. And they usually only have that tail when they're very close to the sun because the sun heats them up and that ice that's on the surface sublimes, which means it goes from a solid to a gas. And that's what we see as the tail. And there are a couple of different types of tails that we see form. There's the dust tail, which is kind of ice and rock evaporating and being ejected from the surface of that comet. And then there's also the ion tail, which is usually created by solar wind. So that's sort of charged particles and radiation coming off of the sun can ionize some of those gas particles coming off of the comet. And an ion is by definition a charged molecule. So the ion tail gets pushed into more of a straight line than the dust tail because you now have charged particles and you have, charged radiation coming off of the sun. So the ion tail is pushed a lot more by the solar radiation because you have, charges interacting with other charges. And then some interesting effects of comets and asteroids on Earth. So I'm sure you've all heard about, asteroids causing mass extinction events, like what wiped out the dinosaurs. That's called the Cretaceous Paleogene extinction event. And that's something that the Earth is at risk for in the future, potentially, because we do have a lot of near-Earth asteroids, and there are still probably thousands more that we haven't detected. But that's kind of one of the effects that pretty much everyone knows about. Everyone knows asteroids can hit the Earth and wipe out life. I think one of the more interesting effects asteroids and comets have on Earth, or had on Earth in the early solar system, was that they're theorized to have brought a lot of the water to Earth that now makes up our oceans. So it was originally thought that comets brought a lot of this water because we knew comets were icy. So we thought that when comets hit the Earth, they would bring all that icy water from the surface. But we now actually think that asteroids brought most of the water, not comets. And the way we're able to tell that is by looking at the ratios of hydrogen to deuterium in the water in Earth's oceans and comparing that to the ratios of hydrogen and deuterium on both comets and asteroids. And with asteroids, that ratio is pretty close. So there's a similar chemical ratio in the composition of water on asteroids to the Earth's oceans. Whereas comets, usually we found, have a higher ratio of deuterium, much higher than the Earth's ocean. So we think that comets maybe brought less than 10% of the Earth's water, whereas asteroids brought somewhere around 80 to 90% of the Earth's water. And then comets, we've also found from the Rosetta probe have a lot of hydrocarbons, which are organic molecules, things that contain hydrogen and carbon. And that's what makes up life on Earth. So we think that comets may have been the progenitors for life on Earth, bringing those complex hydrocarbons to Earth, which then could have developed into more complex microscopic life forms and eventually evolved into modern life forms. Who did this?
Yeah, this is me again. Sorry. So this is one of the comets. This is Chury, we call it. Its official name is Comet 67P Churyumov-Gerasimenko. It was discovered by some Russian person, obviously. And it was originally a Kuiper Belt object with an orbital period of about 6.5 years. And it's only about 4 by 4 kilometers in size. So this is the comet that the Rosetta mission landed on, Chury, and it landed in August. Well, it met up with the comet in August of 2014 and then landed on its surface by November. And it's kind of hard to see from this image. It's not a great image, but what's interesting about this comet is that it's really two comets. And we call this a contact binary. The two lobes of the comet were fused together during a very low velocity collision. So it just kind of got fused together. So we have that cool thing. And yeah, the next slide is the video on that.
All right, so on to more hotly debated topics. Dwarf planets have always been that one little tricky area that people just haven't been able to get a consensus on, and we know this best with Pluto. So before we could kind of figure out what a dwarf planet is, we have to first decide what on Earth a planet is. So the IAU officially defines a planet as a celestial body that, 1, directly orbits a star, 2, has enough mass to be spherical or at least nearly spherical, and 3, it clears the neighborhood around its orbit, which basically just means that there aren't any major rocky bodies or anything within the ring of orbit, and if something is present, it is gravitationally bound to that celestial body. And that's where, unfortunately, Pluto fails because, 1, its orbit does kind of like cross over Neptune, so that's a big no-no for the IAU, and 2, it is considered a Kuiper Belt object, so there are a bunch of smaller rocky bodies that kind of are in this little ring where Pluto orbits and it kind of crosses through. So the IAU definitely thinks Pluto's not a planet. It's been a topic that Astronomy Club members in the past have had mixed feelings about. Some people are very strongly believers that Pluto should still be a planet. So if you want to like have a quick debate on this in the chat, go right at it. But as of now, there are 5 officially recognized dwarf planets in our solar system. There's Ceres, which is an image of that is actually on the bottom right. And that is the only dwarf planet that's located within the asteroid belt. And we have Pluto, Haumea, Makemake, and Eris, which are all Kuiper Belt objects. And oh, I see the chat's going. All right. Anything flat in space is a planet? Sure, we'll say that. Dwarf planets, again, very complicated topic, so we could literally do a whole thing on its own, but that's the basic summary you need to understand. A dwarf planet is basically something that kind of doesn't fit any, like at least one of these qualifications, and it must also not be a satellite. A satellite just refers to any natural body orbiting a celestial thing. So a moon is considered a natural satellite of the Earth. So as long as it's not a natural satellite and it doesn't fit one of these criteria, it could be considered a dwarf planet, potentially. All right, next slide. On to the more cool things, personally, in my opinion, within our solar system, moons. So far, there have been about 160 confirmed moons, and there are many, many more that are still in like that little provisional area where they haven't been officially declared moons, but they're probably going to be at some point soon. A planet or dwarf planet's natural satellite is basic definition of a moon, but funnily enough, there is no formal definition provided by the IAU, and it's to sort of also prevent further controversy, because after the hot takes for the Pluto situation, the IAU really wants to back away and not be the heat of all problems. But two major classifications for natural satellites, aka moons, are regular and irregular. So regular satellites basically refer to moons that generally follow the same plane of orbit as their parent planet, and generally during this stage of solar formation and like solar system formation, whatever material was left over from the planet's formation kind of was around the planet itself, and many times this exact material was kind of coalesced into a moon or multiple moons. And so generally these regular satellites have many similar properties of that little orbital space. They have the same, roughly the same orbital inclination. They follow the similar path. So again, many basic properties are common. And the other type, personally, the more interesting ones are the irregular satellites, because they tend to be either eccentric, inclined, sometimes they move in retrograde, so backwards motion. And usually they're moons that have been captured by their parent planet, and they're kind of like asteroids or any other rocky bodies that weren't supposed to be there in the first place. All right, and the image that we have right now is Enceladus, which is personally my favorite moon because it's really cool. It is Saturn's awesome moon, and what you see on the left side of the image are these water jet plumes that kind of erupt from the hydrothermal vents in the oceans of the moon itself, and it's a very strong candidate, or just a candidate, for life outside of our planet Earth. Next slide. All right, moons. Okay, this is not like a very important thing, but I really like the concept of moons. It's, so far it's hypothetical. It's moons orbiting other moons, because theoretically, there should be nothing stopping it. It's most likely possible for moons that are larger and have wider orbits, kind of giving them enough space so any other tinier thing won't have extreme forces acting on it and causing it to be unstable and kind of spiral into the moon itself or to a planet. So moons, not yet discovered, but I hope for the best, because naming something moon just sounds awesome. And moons in general are one of the best candidates for extraterrestrial life, at least within our solar system, because we really don't expect a lot of life to happen in Jovian planets. And looking at the terrestrial planets, it just seems that moons tend to be like these really nice hotbeds for where life could potentially be found. And one of these places is Europa, which is Jupiter's moon, and the image of that is, okay, Rob's doing the little victory dance. Europa has a beautiful history with our club, because we are, as a club, are trying to make Europa our official moon and replace it with, you know, our beautiful Luna, but we don't need that if we have Europa. Europa, very cool features. So far, we haven't been able to fully document everything, but it is suspected that there is a salty ocean that is beneath Europa's crust, and it actually is suspected to contain more water than planet Earth itself, and it has these hydrothermal vents that are kind of heated by tidal forces, and it keeps the ocean liquid. It has a salty ocean, and there's potential for life being found, especially if there's a lot of organic compounds that are found within Europa's surface. There's also a magnetic field that Europa has that kind of deflects Jupiter's magnetic field just a little bit, even though Jupiter has a very powerful one, which could also sort of prevent Jupiter, or any life on Europa for that matter, to be kind of isolated and protected. I'm going to talk about like 3 or 4 other cool moons. Next slide. All right, Io. Io is a very cool moon. It is Jupiter's moon. I believe it's the third largest, but don't quote me on this. I am bad with remembering things. It is actually the most volcanically active world in the solar system. And as you can see, it's completely filled with these really cool terrains. I'm not a geologist, so I don't know exactly what these are in like detail, but many volcanoes. There's always something spewing out of Io, and it actually has lakes of molten silicate lava that covers the surface, and there's a very thin atmosphere, and it kind of like sends out these plumes that surround the moon itself, and it also kind of trails in Jupiter's orbit. So you see this sometimes when you take different like measurements and images of Io and just the Jupiter systems. All right, next one. Another cool one, moons don't always look the same. They don't always have to be spherical. And this is Hyperion, which is one of Saturn's tinier moons. It looks like a potato, also mixed with a sponge. It has a very unusual, shape to it. Texture is really interesting. And it's actually the first non-round moon to have ever been discovered. And it has very chaotic rotation. It's all over the place. It is also very heavily cratered, clearly. And if you try to look closely enough, and if you go to detailed images, there are like these crater walls that are very bright, and scientists suspect that this might be evidence of water ice formations that are on these craters. So a very weird but very cool looking object, and I personally really like this because it's not the first image you think of when you think of moon, but moons like this exist. So yeah. All right, next one. Charon, Karen, I don't know how you say it. I personally say Charon, but this is Pluto's moon. A lot of people could consider this a double dwarf planet system just because of the large satellite to parent body ratio. It's actually the largest ratio between the parent star, or not the parent star, the parent body, like the planetary body, and its satellite. So that might be like another classification, which is why the IAU never like officially gave any definition for moon. So it could be whatever you want it to be at this point. It is tidally locked to Pluto itself, as I believe Rob mentioned before, like describing what a tidally locked system is. And it has these really interesting formations. And if you see for me, the first thing that kind of pops out is the red color on the top. And that's actually from Pluto's atmosphere. So Charon and Pluto orbit very close to each other. And since Pluto is kind of weak and it's too small to hold its own like a permanent atmosphere, whatever extra nitrogen, methane, and carbon monoxide kind of like goes away and diffuses away from Pluto's atmosphere finds its way over to Charon, and it funnels onto the surface, and over time, as it interacts with UV rays from the sun and cosmic rays, which are just high energy atomic fragments, kind of breaks down and kind of just chemistry stuff and creates tholins, which are complex compounds, and it kind of gives this reddish color. It's found on many other different bodies in the solar system, but again, it's very evident here, and it's a very, very cool looking moon. Mm-hmm.
All right, sweet, this is me. So let's talk asteroid mining. So for those who don't know what it is, this is a 70s artist's concept drawing of what asteroid mining could look like. The concept is that asteroids, some of them have a lot of metals on them. Metals, and I'll go into like which ones later, but things that we could mine in theory and take out of the asteroid so we're not taking them out of the Earth. Can somebody go to the next slide, please? Thank you. So why would anyone think about doing this? We have metals on Earth. So a lot of the mining practices that we have right now do a lot of really nasty things to the environments that they're mined from here on Earth. On the right here in this image, you can see this is a sign in South Africa near a gold mine talking about how the water there is not safe to drink because of the gold mining that's happened. Ecosystem destruction is a big thing, like you can see here in the on the bottom right. This is a mountain range that has been sort of surface mined for coal. There's a lot of other really nasty things that happened. So you can see like sometimes when you mine on Earth, there are things that become toxic once they're exposed to air that have been kind of just chilling under the ground that will all suddenly be brought to bear at once, and they're all exposed to the atmosphere, and now you have a bunch of toxic material. It contributes to water shortages. Like I read this story about in Germany, they had to pump so much water out of the mines that they lowered the water table, which meant that like if you do that enough, you're going to run out of water. And it contributes to human rights abuses, particularly in places in the global south. And we'll get into this on the next slide as well. But there's a lot of exploitation that happens to miners in places because sort of larger, more powerful countries want the materials at a lower cost. And I guess on a happier note, lots of asteroids have lots of water ice, and water is a big component in rocket fuel. So part of the idea is if we can harness this for mining, like some kinds of minerals, why couldn't we just like take a bunch of water ice off of an asteroid and use it to power a rocket? This could be really cool for longer space flights, so that way you don't have to carry all of your fuel into space with you. You can pick some of it up on the way. Next slide, please. Thank you. So like, what could we even get on asteroids? So this is a list of the different kinds of minerals that exist. There's cobalt is a big one that has shortages. You can see a picture of what cobalt looks like on the top right here. And it's like super useful in rechargeable batteries, which is particularly becoming important with self-driving cars or electric cars. And any piece of technology that you have that is rechargeable uses cobalt. And then there's iron. There's starting to be iron shortages, not like less because there is a shortage of iron on Earth, but more because of supply chain things. And those are two very abundant things on asteroids in the solar system. And then this is a list of a bunch of different kinds of metals that we currently mine from the Earth that aren't necessarily in shortage, but have super dangerous and super harmful practices that we use to mine them. Cobalt, again, is a big one. Most of that comes from the Democratic Republic of the Congo, where there's been a lawsuit filed for the deaths of some child laborers that have been in the mines. And there's all kinds of horrible things that happen to the miners, even the adults. So the idea is that if you don't mine on Earth and if you mine in space, you can avoid some of these damages, and you can avoid some of the damages to these communities. And aluminum is on the bottom right. You can see what the ore looks like, is linked to lots of human rights abuses in Guinea as well. So if you do this in space, the idea is that you're not harming the communities on Earth by using these mining practices. So next slide, please. Sweet. So where are we now in this process of like this crazy super sci-fi future thing of mining asteroids? So these are the two most recent missions that we Earthlings have sent to asteroids. There's OSIRIS-REx is the most recent. It launched in 2016. It's going to an asteroid called Bennu in the asteroid belt. And the 4-year anniversary was last Tuesday, actually, of it launching, which was super cool. And 6 weeks from now, it's going to start its first sampling attempt. So you can see it's down here on the bottom, it's over here on the right. The idea is it's using this touch and go sampling method. The idea is it's gonna fly down, it's gonna like drop something down, grab some stuff off the surface and skedaddle, and then it'll come back, and it's slated to arrive back here in 2023. Super cool, super exciting. And then on the left here, we have the next most recent was Hayabusa 2. It is a JAXA mission, so the Japanese Space Agency, that launched in 2014, and it's going to the asteroid Ryugu. And it is sort of this really extensive project, which is really amazing. Like, it released 3 rovers to the surface in 2018 that are doing lots of awesome science. It has, it's going to do 2 sampling runs, and one of them is from an artificial crater that it created. So you can it has this cylinder that it's going to shoot at the surface, and it's going to impact it and bring up a bunch of things under the soil and just kind of disturb the surface, so it can go in and grab some of that debris and we can see what's on the inside. And then it's going to grab some from an undisturbed section just to grab the surface. And it's on its way back now, actually. The sample is going to come back in December of this year, which is super exciting. So these are the 2 missions that we have so far. There have been 12 in total, but these tend to be these are the most ambitious that have happened so far. And we're going to get to see what the composition of these asteroids is like, and it's super exciting. So next slide, please. Right, so let's say that we get the technology to mine asteroids, whether that's from bringing them into low Earth orbit so that we can mine it there, whether that's from just taking the metals back and not messing with taking the asteroid back, whether that's destroying it in space and then running around and grabbing all of the things that we've shot off the surface. However, let's say we have the technology to do this, and let's say it's economically feasible, which it's not right now, but in the future, let's say we figure out a way for it to be. Is this even legal? So the big treaty that's sort of governing this is the Outer Space Treaty that was signed in 1967. That you can see a picture of the ratification and the signing of this treaty on the right here at the UN. And it's, if you've ever heard the language that space is for the providence of mankind, that's where that comes from. This is from the Outer Space Treaty. And it basically says like no country can own any part of space. So there's no, it's kind of like Antarctica in that like there can be no like American parts of space. It doesn't belong to any one country. And any activity in space must be for the benefit of all humankind in the language. But this was in 1967. This was in the Cold War. This was mainly to prevent weapons testing in space. And there's this super huge gap. It doesn't really talk about if you're able to mine in space, if you're able to do resource extraction. Most of the things that we've done in space outside of Earth orbit have been for scientific reasons. And there hasn't been a whole lot of commercial space flight or like space missions yet. But as we sort of move into the future where like this is starting to happen, it's going to be a super interesting gray area where we figure out sort of what it's going to look like. So there's other treaties that have sort of have relevance in space. There's the Moon Treaty, which is very specific on what you're allowed to do in space, but it's only been ratified by 18 countries and none of them have any spacefaring capability. The US is opposed to it as far as I know, and I think China and Japan are also opposed to it, if I read that right. So the Moon Treaty would sort of forbid this, I believe. The idea is that you're not, like private companies can't do things for profit in space is one of the tenets of the Moon Treaty. But that hasn't been ratified by any country that has spacefaring capabilities. Then we have a couple of other treaties that govern what you can do in space. There's the Rescue Agreement, which deals with what happens if astronauts get stuck somewhere and you need to rescue them. There's the Space Liability Convention, which is like what happens if your space mission damages another country's satellite or it crashes on somebody's house, or like who is liable for that. So that's what that deals with. There's the Registration Convention, which it looks like a lot of red tape and is kind of like, how do you actually, like, what is the paperwork for all of this and what does the documentation look like? But there's not any regulations that would be super relevant to asteroid mining as far as we know. So in summary, this is like technically legal. It's very much a gray area with the Outer Space Treaty of if you can really define like asteroid mining to be for the providence of all mankind, if it's a private company that's mining it. So it's an interesting gray area, but there's nothing technically stopping it as far as I know. So a couple of you asked about asteroid mining in the survey in like the weekly thing. So that's the deal with that. Next slide.
All right, that's it for our presentation for today. So thanks everyone for coming. We do have another activity after this. We're going to play a quick Kahoot based on a lot of the information we just learned in the presentation. So if any of you do have to go now, that's fine. But if you'd like to stick around and join us for a Kahoot, I'm getting that set up right now, and I'll have it ready in a minute or two.